Hey, welcome back to Fat Mama Physics. This is the last video in this series on exponential decay and half-life. So we have two examples that will use the equations that we have derived and the relationships that we found with this natural ln graph in terms of what the y-intercept means, which is the ln of the number of original radioactive nuclei, and the gradient, which is the negative of the decay constant. Okay, so let's go. Number 5. The half-life of a radioactive isotope is 10 days. So I'm going to write this as half-life. Looks like that. Calculate the fraction of a sample that remains after 25 days. So this is going to be the time that elapsed. So first of all, we have the half-life, which is 10 days. So two things you could do is you could use the original equation to figure out the decay constant, which is what essentially you have to do. And of course, if you've derived the equation of the half-life already, which apparently you probably have to do anyways on a test. So on a test, you have to be able to show this. You can't just one-off use this equation here. Since it's not from your data table, IB exam probably will not give you marks unless the question is sometimes the marking scheme will say give the full marks if for a bold answer, which I don't think they'll do for this case because they actually want to see if you can manipulate this kind of equation. All right, so assuming that, what we can do is let's just take the original equation from your data table and use that to figure out the decay constant. Okay, so first of all, we know that for a half-life, the ratio of n to n naught is going to be a half. Okay, and then after we arranged it, the other side of the equation is going to look like e to the power of negative lambda t, in which this t is just going to be the half-life, and this is what we need to solve. Okay, so essentially you are doing question number 2. Okay, so I'm going to write a note here. See example, okay, example 2. And after you show example 2, after you do solve for the decay constant, you're going to get the decay constant is going to equal to ln 2 over the half-life. Okay, ln 2 over half-life. Ln 2 over half-life is, for us, is going to be ln 2 over 10 days. And you don't have to be worrying about converting 10 days to seconds because your decay constant will be whatever number days to the power of negative 1. So ln 2 divided by 10 is going to give us 0.0693 ... and this is going to be days to the power of negative 1, okay, per day. So, and that's okay because the time that we have to eventually use anyways will be in units of days anyways. So to find the fraction of the sample, this is n over n naught is equal to e to the power of negative, and guess what? We know the decay constant now. The decay constant is 0.0693 ... and I am going to show the units per day, okay? Because that's going to cancel out with the actual time, which is 25 days. Okay, so notice that I plugged in lambda, which is 0.0693 days. The units is per day, and the time, which in our case for this equation is 25 days. So the days here, the units cancel out, which is just to show that it didn't quite matter if you converted your half-life into seconds or not. Essentially, as long as the units with the time matches up when you calculate for the fraction here, then that's okay. So I essentially just take this number, I times 25, I make it negative, and I take e to the power of that number, and that's going to give me the ratio. Okay, so this is going to give me, oopsies, 0.17677 dot 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 dot, and the answer key is wrong. This is going to give you percentage with, let's say 3, or actually let's say do 2 sig figs. That's going to be 18%. Okay, all right, so there you go. That is 18%. Woohoo! That was the first example. Okay, so the number 6. Ooh, number 6 looks a little trickier. The graph on the right shows the relationship between ln C and T, where C is the activity of a radioactive substance and T is measured in hours. Okay, so there's a lot of things we have to find here. We have to first find the half-life of the sample, the sample's initial activity, and the activity after 1 day. So 3 things to calculate, all from one graph. So we should get down to it. So to work this out, we actually should use this equation here with the activity instead of the number of nuclei. So we're going to go ahead and do that. So starting with this one, activity is equal to lambda n naught e to the power of negative lambda t. I'm going to show, I'm going to work this through to take the ln of both sides to essentially show what the y-intercept means, what the slope means here. But also, I want to combine these two terms. We know that lambda times n naught is also equal to the initial activity, which kind of makes sense. The initial activity, after some decay happens, is going to give us the final activity. So in fact, I can rewrite this as activity is equal to, actually write it here, activity is equal to the initial activity times e to the power of negative lambda t. So let's take the ln of both sides of this equation. We are going to get the following. Ln A for the activity, actually it's just going to be C, because that's what it changes to. This question uses activity as C. So maybe just to make it less confusing for us, I'm just going to change that to A. So we get ln A is equal to ln A naught e to the power of negative ln t, lambda t. Don't forget, if two things are multiplying here, these two powers, we can split them up into ln A naught plus ln e to the power of negative lambda t. So that after doing a bit of after solving this, and hopefully if you've watched the previous video, this is essentially me dropping negative lambda t down in front, and then I'm going to get ln of e, oh fine, I'll write it again, negative ln t, and then this is going to be ln of e, this is going to be equal to 1. Which then will disappear from this equation. So what we're going to be left with is ln of A is equal to, I'm going to put this guy in front, negative lambda t, and this has to happen, so we get plus ln A naught, and which we have just shown comparing this to y equals to mx plus b. The b value, which is the y-intercept here, this is essentially the ln of the initial activity, which is going to be useful later on. We also know that the gradient is also going to be negative of the decay constant. So it's very similar to our previous situation, okay? So now that we know that, let's solve for a few things. First of all, we can analyze the y-intercept. It's probably the easiest to do first. So we know that ln A naught is 4.6, okay? And meaning if we want to solve for the initial activity, we just, using the definition of the natural logarithm, e to the power of 4.6 is going to give us our initial activity, and that is 99.48 becquerel, or that's going to give us rounded to, let's see, maybe 2 sig figs. This is 99 becquerel. And I'm going to save this number because we're probably going to use this later. So that's for analyzing the initial activity. So we got this already. We want to figure out the half-life and the activity after 1 day. So to do that, we need the decay constant, which is analyzing the gradient. So to get the gradient, we need 2 points on this graph. It is very easy just to take the first point and the last point, since they lie very nicely on the grid lines. So this gradient here, and I'm not going to take the fact that it's negative because I just need the positive decay constant to help me calculate this. So to calculate decay constant and not caring about the negative sign, I'm going to take the height of this triangle, which is essentially 4.6 minus whatever this is over here. This is 4.1, so that's going to be 4.04, okay? And then divided by the base of the triangle, which is all the way to 10 hours, okay? So this is 10 hours. This is going to give us 0.056 hours to the -1. So that's our decay constant. To figure out our half-life, I'm just gonna write a note here. See example 2. I'm running out of space. So our half-life here is just ln of 2 over, ln of 2 over our decay constant, which we have already. And on an actual IB exam or a question, you would actually have to show that this is the case. So just to repeat that again. So putting everything in, I'm going to put ln 2 over 0.056 hours to the -1. This is going to give us 12.377, which rounding up to 2 sig figs, that's just 12 hours. And the reason why it's in hours is because if you take the inverse of hours and it's the inverse, the reciprocal, this reciprocal is going to get hours on top. Okay, so that is for the decay constant finding us half-life. We still need a decay constant to help us find the activity after 1 day. Oh, okay, so notice that's 1 day. Okay, so using activity is equal to initial activity times e to the power negative lambda t. The initial activity is going to be 99, blah, 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 whatever that is, e to the power of negative decay constant, which is 0.056. This is where we have to be careful. This is in units of day, this is hours. Hour to the -1, but then we want 1 day, which is actually 24 hours. So this is where we have to match our units to make sure that the units cancel out nicely in our exponent. So if we do all that, we're gonna get, don't forget the 99 is a saved number, which I have all of my saved units. E to the power of negative, don't forget that negative sign, sometimes students will forget that, times 24, this is going to give me 25.9 becquerel, 25.9, rounding up to 2 significant figures, this is going to be 26 becquerel. And there we go. This is our whole question. A lot of space taken up. So this is essentially our exponential decay. So notice that from doing all these questions, you really need to know how to operate your logarithms and natural logarithm rules. Okay? So hopefully you got something out of these videos. I wish you the best of luck. And Fat Mama Physics signing out.